Okay, so let's start today's class. So in this class we will learn about also the syntaxes of SystemVerilog. Okay, so so in the previous class we learned about sorry about that. Sorry about my status. So we learned about the combinational Laplace, and then so in this class we will learn how to implement combinational blocks using SystemVerilog. Okay, and then we will learn about the new syntaxes or new statement in SystemVerilog. Okay, so this is actually very important. So we will use these statements very frequently in SystemVerilog. Okay, so always statement. So when you learned about the SystemVerilog, so actually we firstly learned about where is the assign statement. So and then I explained that the assign statement assign statement means implicit continuous assignment. So which means that the right hand side value or right hand side signals are continuously assigned to left hand side variables or left hand side signals. That is the meaning of assign. Okay, but so now we will learn about the always statement. So this is the syntax. Also, this is the definition. So which means that you need to memorize. You need to memorize the definition of this statement. So it's same. So actually, if you learn about some programming languages, then you need to memorize. You need to memorize the definition of statements or syntaxes or operators. So it's the same. So always statement. So definition of always statement is that so whenever the event in sensitivity list. So if you see the structure of the always statement, then you can observe sensitivity list. Okay. So always, so this is the structure of the always statement. So it's always, and then you can find some symbols. So this is the symbol represent the certain event. Okay, and then you can find the sensitivity list. So always a statement represent that if the events in sensitivity list occur, that's true, then the statement inside of always statement are executed. So if this event occurs were true, then the SystemVerilog execute this statement inside of the always. So that is the definition of always statement. And then in SystemVerilog, we frequently use always statement. It's very important. So you can find the begin and end. Okay. So we need to use the begin and end if the statement inside of always are multi-line statements. Okay. So it's similar to the practice in C. So if we use, so you are familiar with the C, then I believe you already know that if we use the like a for statement like this, okay, there are multiple lines inside of the for statement, then we need to use the brackets, right? In C. And then actually in SystemVerilog, we need to use the begin and end. Okay, it's similar to the brackets in C. Okay, so you need to remember that if you use multiple statements, multiple lines inside the already statement, and then it's also other statement, then we need to use the begin and end. Okay. So actually this is the definition of always statement in Verilog actually. So so you can use also this traditional always statement in SystemVerilog because SystemVerilog includes features of Verilog. So this is the superset. SystemVerilog is the superset of Verilog. Okay, so you can also use the traditional always statement. But in SystemVerilog, there are three different kinds of always statement. So as you can see, you can find the always underbar com. So it means that we can use this always underbar com for implementing combinational logic. Okay, and then also you can find the always underbar ff. So actually we did not learn about the sequential logic yet, but we can use the always underbar ff for implementing sequential logic. Okay, so we will learn about the sequential logic later. Okay, maybe the next class. And then we can use the always underbar latch for implementing latch. We also learn about the latch, maybe next class. So it's a kind of sequential logic. So just remember the always underbar com for this class. So we can use the always underbar com for implementing combinational logic. So actually the meaning of always underbar com is same to the always at star sign. Okay. So if we use this symbol, so it represents the everything, right? But actually, if we use this star symbol or asterisk symbol inside of the sensitivity list, then it means that this always statement automatically generate the sensitivity list based on the input signals. So then always if the input signal values are changed, then the always statement will be executed. Okay, actually this is same to the always underbar com. Okay, so for implementing combinational logic, so you can simply use always underbar com. Okay. Okay, let's see the example. So I believe this module is very familiar with it. This module is familiar, right? Because so actually this module implement the multiple bitwise operations, right? Like there are seven output ports, and then the width of each port is 4 bit. Okay, and then also you can find the 2 input ports. So, and then this is this module exhibit some different kinds of bitwise operators in SystemVerilog, but we use the always statement. So actually in the previous class, so here, yes. So we can implement this bitwise operations using assign statement. Then what is the meaning of assign statement? Actually, this right-hand signal is implicitly assigned to the left-hand variables, left-hand signals. So which means that if this right-hand signal is changed, the value of right-hand signals are changed, then the SystemVerilog recalculate the output of the right-hand signals, then update the left-hand signal. That is the meaning of assign statement, right? So actually, this is actually So you can, so this module is equivalent to this module implemented using always statement, right? So, so you can find that, so this is the left hand signal, and then this is right hand signals, right? But you can find that, so the assign statement is missing for this line. So every line assign statement is missing. Okay. So but you can find that, so these statements are inside of always underbar com statement, right? So you can find the begin and end here. So it's kind of brackets. Okay. Then you can find multiple statements, multiple lines of a statement inside of the always underbar com. So what is the meaning of these statements? So actually the operation is the same. So operation is the same to the previous module, right? So the module that use assign statement, the operation is just equivalent, but we can use the always statement like this. Now what is the meaning? So I mentioned that this is equivalent to always at start. And then this means the everything. Okay. So if you see the statement inside of the always, then you can find that these signals are input, right? What are inputs? A and B. So you can find that A and B are inputs of the statement inside of always underbar com. So the meaning of this sensitivity list mean is this is the all inputs for this already these statement. So what are all inputs? All inputs are A or B, A and B. Okay. So actually, this is also equivalent to the always add A or B. So the sensitivity list I use or because if A is changed or B is changed, that means if A is changed or B is changed, because so I use or here. But instead of this, so we can use this always statement. So it's more convenient. So also we can avoid bugs, okay? Because we don't need to specify some input signals in the sensitivity list. Also, we can use always underbar com in SystemVerilog, okay? So which means that we can easily implement the combinational logic without specifying input variables or input signals. Okay, we don't need to specify sensitivity list for implementing combinational logic. Okay, so we can just use the always underbar com. So this is same. The meaning is the same. So if the A or B are changed, then these statements, the statement inside of this always block or always statement are executed. Okay, so these statements are executed if A or B are changed. Okay, so it's the same to the meaning of this. But the difference is that actually for the assign statement, actually each line, so like so actually the output is the same. So I said that output is the same, but if we use the assign statement, this assign statement is effective for only this line. Okay, so which means that the multiple assign statements are executed in parallel. So this assign statement is only effective to this line. But if we use the always statement, this always statement is effective for this multiple lines because we can find that always statement includes these statements. So if the sensitivity list, the event in the sensitivity list occurs, so which means that A or B are changed, then these statements are executed. Okay? And then, so we do not learn about the sequential or the blocking or non-blocking in SystemVerilog, but actually inside the always statement, these statements are executed sequentially from top to bottom. Okay? Sequentially. So in SystemVerilog, so SystemVerilog execute these multiple statements sequentially. So firstly, this is executed, this is executed, this is executed. But because each output is determined by multiple inputs A and B and independently, so we can say that the outputs are the same, right? So it may be tricky because so we can implement the same logic or same combination of block using always statement or in assign statement. But you need so in SystemVerilog, the execution is a little bit different. Okay, so as I mentioned, so assign statement is just effective to one line, so one statement, and then the multiple assign statements are executed in parallel. Okay, in parallel. But inside of the always statement, and then if we use the just equal sign, then multiple statements are executed sequentially from top to bottom, like the normal programming language. Okay, but actually it's equivalent. The output of this always statement and then the previous assigned statements are equivalent actually. So I also I hope you can review the slide, like the slide, so you can also read the comments like here. So I also added the comments for this code. So and then for the multi-line comment, you can use this sign, okay, in SystemVerilog. So if you read this comment, the always come statement need begin end because there are more than one statement. Okay. So you can also read the comments inside of the code. Okay. So as I mentioned, so we can also implement the equivalent module using assign statement. Okay. But so actually this is just a recommendation. But if we just implement the pure lines of statement, then we can use the assign statement. So it's simpler, okay? But you can use any statement, like so you can use the always statement. Also, you can use assign statement for implementing combination logic. But if you implement very simple, like the one line statement, the very simple combination logic, then it is it is recommended to use assign statement because we can use just one line if we use the assign statement, right? So in this okay. Also, so I am sure. So this is actually the Verilog code. So uh, so the problem is that so actually many companies, many industry companies still use Verilog. Okay, so Verilog is Verilog has the longer history than SystemVerilog also. Actually, Verilog is the subset of the SystemVerilog. So this is the Verilog, and then this is SystemVerilog. Okay, so it means that you can also find the Verilog code frequently in the internet. So if you just search some codes in the internet, then you can actually, I believe you can frequently find the Verilog code, not SystemVerilog code, because the Verilog has longer history. So we can also implement the same code using Verilog. So this is the example. Actually, this is the same code, but you can find some differences, like the output signals are declared as reg type. Okay, so you can find the sensitivity list here. Okay, A or B. So you can also you can use this star symbol for inside of the sensitivity list, but you cannot use always on the com in Verilog. Okay. Okay. So difference is that so output variables are declared as reg. Then this is the same. The statement inside of the arrays is same, right? So actually, if you use Verilog, then if these variables are driven by some inputs inside of arrays statement, then these variables need to be declared as reg type. Okay, so in Verilog there are two different types for some signals, so logic signals. So in Verilog we can use the wire or reg. Okay, but in SystemVerilog we can use logic type. Right? So it's a simpler. So in Verilog, we need to distinguish wire type and reg type. And then in Verilog, if some signals are driven inside of array statement, then these signals need to be declared as reg type. Okay? But so this is the Verilog. But in SystemVerilog, we can just use the logic, the same. So SystemVerilog does not distinguish wire type or reg type. Okay, so it's simpler, right? So this is the example. But as I mentioned, the Verilog has longer history. So then you can just you can read some Verilog code. Okay. Okay, so this is the always statement, and then let's learn about the if-else statement. So if-else statement, so we frequently use if-else statement in C or C++. Okay, that's because so if-else statement represents that. So it's very simple. If the condition, so you can find the condition here. If the condition for the if statement is true, then the statement A is executed, so S, then if the condition is false, then state B is executed. So it's the same. So in C, we can the code like A, bracket, then statement, else, bracket, and some statement like here in C. But actually, as I mentioned, the syntax of SystemVerilog is very similar to the syntax of C, right? So if S is the same, so if the condition is true, the statement A is executed, else the statement B is executed. It's simple. Okay? But also, if you use the if else statement, then if else statement needs to be used inside of always statement. Always, okay? Always statement. So we cannot use if else statement with assign statement. So if you want to use if else statement, you need to use the array. So this if else statement needs to be used inside of array statement. Okay. And then, so this is actually very important. So actually in C, like any programming language, it is allowed, like if A is the condition like this, then C equal A minus B, like this. Then, so, and if you see this code, else condition is not defined, right? So what does that mean? If A is 0, then this statement is executed. If not, nothing is executed, right? So we can write a code in programming languages, right? In any programming language, so like this. But in SystemVerilog or Verilog, if we use if statement inside of arrays to implement the combinational blocks, then we always define the else statement. So which means that so you need to also remember that we use SystemVerilog or Verilog to implement hardware, right? So it means that the Verilog code or SystemVerilog code needs to be synthesized into hardware module. So which means if else statement is the same, if we use the if else statement, then this if else statement needs to be translated or synthesized into hardware. Which means we need to implement correct hardware using Verilog or SystemVerilog, right? So problem is that if we do not define the else condition, then this array statement will implement latch. Okay. And then usually if latches are synthesized, latches are generated by SystemVerilog, it means bug. It's a critical bug actually. Okay. So you need to remember that if else condition should be defined for all possible input conditions. Okay. All possible input conditions. So which means that if we use the if else statement inside of arrays on the com, the combinational logic, then you need to define the statement A, statement B, or C, or D. You need to define statement for all possible input cases. Okay, this is very important. Okay, otherwise, latches will be generated, and then this means bug. Okay, latches are generated, that means you generate bugs. Okay, it's very critical. So when I learned about this SystemVerilog from other professor, then he mentioned that if the latches are generated, that means sim. It's a function. Okay, so if bugs are generated in your code, that means it's a sim. Okay, it's a sim. Okay, so we need to avoid bugs in our code. Okay, so let's see the example. So this is the example, and then this is the example on the bug. So which means that you can understand that this code will generate. This code includes bugs, okay, and then this code will actually generate latch. Okay, so why? Let's see this code. So this is always on the com statement. So this is the always statement for combinational logic, and then you can find the if statement here. So if A is equivalent to 0, statement A. So we define the statement for input A equal 0. A is the 2-bit signal, right? And as if A is 1, then statement B is defined. So we cover A is 1. And then as if A is 1, 0. So 1, A is 1, 0. Then statement C is defined. And that's it. What's the problem? Problem is that A is 2-bit signal. A is a 2-bit signal, which means there can be 4 different cases, right? Like 0, 0, 0, 1, 1, 0, 1, 1. Okay. So in this code, I define the statement for 0, 0 is A. Statement for 0, 1 is a statement B. Statement for 0, 1, 0 is a C. But this condition is not defined. So you need to remember that if we use if-else statement, then we need to define. We must define all statements by all input cases. So if not, this is a bug. So this condition is not defined inside of the always statement. So latch will be generated. It's actually bug. Okay, it's incorrect hardware. Okay, so it's very important. We need to avoid generating latch. Sometimes we can generate latch, but it's very special case. Okay? Okay, so if we use the multiple statement inside the if-else statement, then also you need to use the begin and like this. So you can just understand that begin and is similar to the brackets in C. Okay, so we learned about the if-else statement. So then let's learn about the case statement. So case statement is actually very similar to the switch in C. Okay. So actually we can, so for the input A, we can define some different cases like this. Different cases using if-else statement. That can be possible. But so it's actually it's the same. So we can also implement some very the repeated if-else use if-else statement in C. But if we use the switch statement, then we can write code it's in a simple way. In a simple way, right? So it's the same. So actually case statement is so case statement is similar to the switch statement in C. So which means that we can just define the input values or input conditions using the case statement. Then we can also list the output, the statement by the multiple inputs. Okay. So it's very important to define default. So let's see the example. So this is the example of a case statement. Okay. So also you need to use case statement inside of the already statement. Okay. You cannot use assign statement. Okay. So inside of the already statement, so already on the com, then so it starts with the case and variable. Okay. So like so if we use A, then we can just use the variable A inside of this condition. Okay. And then if the condition is 0, so it means that if A is condition 0, then statement A will be executed. So if the condition A is the equivalent to condition 1, then statement B will be executed, 2, C will be executed. Okay? And then this is important. Then we can also define default behavior for case statement. So which means case statement is the same. If we just define conditions for this variable, then we need to define all possible conditions. All possible conditions for this variable A. Okay? If not, latch will be generated, and then that's a bug. Okay? So in the case statement, we can just simply use the default statement for the otherwise conditions. Okay, like this one. So if the otherwise condition, like A is the some other default otherwise conditions, then statement D will be executed. Okay, so just remember that in the case statement, it is recommended to use default statement. Okay, so it means the otherwise. So it covers other conditions. And then you need to remember that if we use the case statement, then these conditions need to cover all possible values of this variable. Okay, if not, that will be generated. So this is the example. So case statement. So this is the input, it's a number, so it's a 7 segment. Okay, so it's 7 segment is like looks like this. So if you see the old calculator, then you can find some LCD line. So it's actually the liquid crystal, but actually the you can just turn on or turn off this simple line, so 1 line, or enough to represent some numbers. Okay, so this is the 7 segment logic. So which means that it just represent some values using the 7 segment, like some okay, like this. So this logic receive input signal like number, okay, and then the output is the 7-bit output, because if you count the number of SD bars, then you can find that there are 7 bars. Okay, so this is the always come statement. Then it starts with the case, and then as you can see, norm is here. Okay, it's a variable. Okay, and then I just define the output. Output is the set. So output value by input signals. Okay. So actually, we can just display 0 to 9, number 0 to 9 using 7 segment, right? So because we use the decimal number system, right? So you can define the output until 9. And then if we do not use the default value, then it's bug. It is because the norm is the progress signal. So which means that this norm can have 6 different cases, 6 different values, right? Because the progress signal. But we can just define until from 0 to 9 using this 7 segment logic, but we also need to define other values for norm signal, even though this is not defined, but in the logic, in order to implement this logic using hardware, then we need to define all cases, all input cases. So in the case statement, we can use the default. Okay, we just define the values from 0 to 9, then otherwise we can just use the default. Okay, then output is 000. It's required. Okay, if not, then it's a bug. Okay, it's very important. Then, actually, if you define the default values, then we can also use the don't care. So if we just compare this slide and then this slide, so the only difference is that for the default case, then output is for this slide, the output is defined like as all zeros, but in this case statement, outputs are defined using all don't cares. Okay, like X. So you can find the don't care here. So what is the better design? So this is the code case code one. Okay. So in this code, we just define, so we need to define the default value, right? Default case. And then for the default cases, then output is driven by all zeros. Okay. And then there's code two, then we just use don't cares. Okay? Because we do not expect the other input values. So we can just define the input values from 0 to 9. That's enough. For the other values, we don't need to define. So we can use don't cares. Okay, but which is better hardware design? Which is better? So we learned about the kernel map, right? So and then if in the kernel map, so we can build kernel map based on the truth table, right? So you can understand that this is the output, okay? The output of the truth table. So if we just generate the truth table based on this logic, then so this is the A0, A1, A2, A3. Then we can make the truth table like 0 to 9, like 1, 0, 0, 1, and then 1, 0, 1, 0, and then 1, 1, 1, 1. So this is the output, like the Y0, right? And if we just write some values like 1, 1, 0, 0, 0, 0, or we can write the value like don't cares for the output. Which is better? Which logic is more optimized? So if we use the don't care, if we use don't cares, then this logic will be more optimized. Right. So we learned that in kernel map, for the X like don't care, then we can use any values, 1 or 0, but we can use more optimized values. We can select the values that can make more optimized result, right? For kernel map. But if we just define some specific value like 0, then we can just generate only one case. And this is not optimized. So if we can use the don't care, then you can define the outputs using don't cares. Then the hardware logic will be more optimized. Okay. So code 2 is better because code 2 will generate the more optimized hardware. Okay. So, and then so if you see this slide, so you can find that this is bug. Why? So it's the 7th set of the bug. So why? Why is it this bug? Because as I mentioned, I just defined the 10 cases out of 16 possible cases. So if all cases are not defined inside of this already statement, it's wrong. Okay, so this is wrong. So in a case statement, that if you it is recommended to use default statement always. Okay, default statement. So we need to avoid bugs. Okay, so in order to avoid the bug, the case statement, then you need to use default statement. Okay, so it's bug. And then, so this is another case statement like the case Z. So if we use the case Z instead of case, then you can use don't care as input. Okay. So what is the difference? So in this code, so I use the case Z, and then this is the input variable, right? And then in this case Z, I just use the question mark inputs. And actually, in case Z, this question mark represents the don't care. So this is don't care input. So which means that if the A3 is 1, then this is the output. So you know this is the priority decoder, right? And then in the priority decoder, then we can define the behavior of priority decoder using don't care, right? So we love. So if we use the case Z, then we can use the don't care input for this condition. But if we use the case, then we cannot use the don't care inputs. Okay. Okay. So then, so let's see how to implement some basic combinational blocks using SystemVerilog. So let's start with the multiplexer. So 2-to-1 multiplexer. Okay. So this is the SOP form of the 2-to-1 multiplexer, right? Okay. So as you can see, so this is the selection signal and the two inputs, and then based on this selection signal, input D0 can be selected or input D1 can be selected. So if the S is 0, then if S is 0, then this becomes 1. So this AND gate is activated. So D0 is connected to the Y. And then if the S is 1 and this AND gate is activated, so D1 is connected to Y. So Y becomes the D1. So this is the combinational logic. Combinational logic implementation of 2-to-1 multiplexer. But we can use the SOP form. So we can implement this multiplexer like this using SOP form. So this is the SOP form. So this is the AND gate, right? These are AND gates and then OR gate. Okay, so it's simple. So this is 2-to-1 multiplexer. And then we learned that we can also implement 2-to-1 multiplexer using tri-state gate. So this is the example. Okay, so we can use the tri-state gate, and then if we use tri-state gate, then output needs to be declared as a tri. Okay, so tri-state will generate the high Z signal. So high impedance is disconnected. Then the outputs are connected. So like this. So this is the another implementation of 2-to-1 multiplexer. Okay, you can use the tri-state gate. This is the example code in SystemVerilog. And then another example, and then actually we can simply use the ternary operator in SystemVerilog. Right. So actually it's a definition. So if cell is 0, then y equal a, else y equal B. So this is the definition of 2-to-1 multiplexer, right? So actually, we can just simply implement this 2-to-1 multiplexer using ternary gate. So it's the same. So this is the selection signal. Okay. Then if the selection is 1, then which one is selected? D is selected. So S here. And then if the selection is 0, then A is selected. So actually, 2-to-1 multiplexer is very simple logic. And actually, we can implement this 2-to-1 multiplexer using 1-9 assigned statement. So it is recommended. So if we use the smaller number of 9, then it is recommended. So we can simply implement this multiplexer using ternary operator. Okay, it's very simple, right? And then we can use the assign statement because it's the ternary operator. And we can also use if else statement, right? So we learned about the if else statement in this class. So we can implement the 2-to-1 multiplexer using if else. So simple, right? It's by definition, if the selection is 0, then y equal A, else y equal B. This is not about because I just define all possible cases, like selection is 1 and else. So conditions of this if else statement covers all possible cases, right? So this is not about. So this, and then as you can see, this is the 2-to-1 multiplexer, and then I use the arrays on the count. Okay. Then how can we implement the 4-to-1 multiplexer? What is the 4-to-1 multiplexer? The 4-to-1 multiplexer is that there are 4 inputs A, B, C, D, and then the selection signal has the 2-bit signal, 1 down to 0, then 1 output. So based on the selection signal value, the one of inputs is connected to output Y. Okay. So how can we implement this 4-to-1 multiplexer? So this is the example. We can also implement this 4-to-1 multiplexer using 1-9 using 1-9 assign statement. So this is the example. So Y and so we also use I also use ternary operation. Okay. So firstly, we check the output using selection 1. Okay. Selection bit 1. Then there are 2 outputs. So but inside of this statement, so you can find the another ternary operator here. Right? And then the output is determined by this selection 0 signal. So actually it looks like this. Okay. So firstly, so it's A and B. It is selected by 0. Also C and D is also selected by selection 0 bit. Right? So you can find the selection 0 and selection 0 here. And then this output is selected by selection 1. And this is the output. So this assign statement just represent this logic. Okay. Right. Okay. So we can implement this 4-to-1 multiplexer using multiple ternary operators. And then we can also simply use the nested nested ternary operator. So like this. So actually ternary operator is like it's if else. It's the same to the if else. So 0 A is selected. Else if 0 1 B is selected. If else 1 0 C is selected, and then D is selected. So it's the same. Actually, the output is the same, but it's a little bit different because if we use the nested if else statement, so this is the nested if else statement, right? So firstly, we check the 0 0, and then we check 0 1, and then we check 1 0. Even though the output is the same, I mentioned that if firstly if we check 0 0, and then we check 0 1, and then we check 1 0. So what is different? I mentioned firstly, and then secondly, and then third, and then implicitly I firstly check 0 0. So we can observe priority. So you can find implies priority because 0 0 is firstly checked compared to other possible cases. So it means that this nested if else actually implies priority. Firstly checked, and then secondly checked, and then thirdly checked. Okay, so slightly different. Okay, even though the output is the same, the meaning is slightly different. So actually it looks like this. So A the 0 0, not this one. C it looks like this. So D, and then it is checked by 1 0 selection, and then it's a B. B is selected checked by selection equal 0 1, and then A is selected like 0 0. This Y. Okay. So as I mentioned, the output is the same, but the meaning of this nested if else is it's equivalent to this hardware, and the meaning of this implement this hardware is actually this hardware. Okay, little bit different. Okay, little bit different, but implies priority. So as you can hardware is different. Okay. Okay, so we can also use the arrays statement for implementing 4-to-1 multiplexer. Okay, so we can simply use the case statement. So actually the case statement is, so we can easily and then simply implement multiplexers using case statement. Okay, like so this is the selection variable, and then it's 0 0 y equal A, 0 1 equal B, 1 0 equal C. Important default y equal E. So this is the case statement. So actually this case statement is equivalent to this nested if else. Okay, so actually we can find the hierarchy. We can, so this nested if else implies priority because the 0 0 is firstly checked. It's the same because the case statement is also equivalent to switch in C, and then the meaning of switch is the same. Firstly, 0 0 checked, else 0 1 checked, else 1 0 checked. Okay, case statement is the same. Okay, but which hardware is better? So I repeatedly ask, which hardware is better? This one or this one? Which hardware is better? This one, number one, number two. Number one is better. Number two is better. Yes, you are right. Number one is better. Why? If we just compare the cost, actually the cost is the same, right? So actually this first hardware uses 3 2-to-1 multiplexers, and this hardware uses 3 2-to-1 multiplexers. The cost is the same. And what's different? The first is delay. So which one is faster? This one is faster. Why? Because from A to Y, we can just pass through 2 multiplexers, right? But for the C to Y, for this hardware, from C to Y, we can find 3 multiplexers. So when we calculate the delay, we can just accumulate the delays of the logic gates in the past, right? We just accumulate. We can just add the delay of logic gates to calculate the delay from input to output. So which one is so this hardware 2 delay is longer because from C to Y we need to pass through 3 multiplexers. Okay, but this logic from C to Y is the same. We can pass through 2 multiplexers. So this one is faster. And everyone wants faster hardware, right? So hardware 1 is better. But we know that we can, if we use the case statement, then we can easily implement the multiplexer. But we want implement the multiplexer like this. Okay. Actually, for the multiplexer, we cannot find any priorities for input signals, right? But if the multiplexer is implemented like this, then we can observe priority. Okay, so we can add primitive. So in this, this is a comment, right? So it starts with the comment. It is declared like a comment, right? But this is the special comment. Okay, like this is a full case and parallel case. Okay. So it means, so actually when the SystemVerilog is simulated, this comment is ignored. Because it's just a comment. But when the SystemVerilog code is synthesized, the synthesized means it's translated into hardware, then the synthesis tool check the primitive. So it starts with the synthesis, okay? So it means that this is the synthesis primitive. Okay, then synthesis to read some primitive inputs, and then the synthesis to generate hardware based on this primitive input, primitive condition or parameters. So it mentioned it's the full case. So it means that the full possible conditions need to be defined and parallel case. So parallel case means that so A, B, C, D. Actually, we do not generate any priorities for these inputs, the different inputs. So we want to generate the hardware like this, right? But if we use the case statement, then actually I mentioned that case statement is equivalent to this nested if else. Okay, so we can find priority. But when the hardware is generated, then this priority is just ignored. So if we use this synthesis primitive, then synthesis to generate the photon multiplexer like this hardware. Okay, because it's a parallel case. It's a full case and parallel case. So the hardware is generated like this. So that's why the SystemVerilog is a little bit tricky, because the simulation can be different from the generated hardware, which is synthesized hardware. Also, SystemVerilog has a kind of the synthesis tool primitive, like this one. Then the synthesis tool with the primitive parameters or primitive commands, then generate the hardware based on the synthesis primitive. Okay. So you need to remember that. So this is the hardware language. So simulated code, simulation behavior can be different from the generated hardware. Okay, so also we can define some target hardware model. So interesting, right? So decoder. So you can find the decoder. So we can also implement the decoder using this statement, like case A. So define. So this is the input. So this is the truth table of the decoder. Then, so this is the input and this is the output, right? So we can just define the outputs based on the all possible inputs, 0, 0, 0, 1, 1, 0, and default. So you can use the 2B11 here, because if even though we use this 2B11, then we can define all cases, but it's a good practice to use default here. Okay. So default y is 1, 0, 0. So it's equivalent to 2B11 and y equal 4B1, 0, 0, 0. So it's equivalent. Okay. It's a decoder. Okay, so so in this time, so we learn how to implement the combinational logic using SystemVerilog. Then I'll stop here. Then the next class, so we will learn about the delay, and then so we will learn about the sequential logic. Any questions? So thank you for your attention. See you in the next class. 감사합니다.